Hello, everybody. Today we're going to start a new unit in math, and it's one that's going to be with us for quite a bit of time during this year. It's called functions. And functions are used for modeling and predicting change because the only thing that is constant in life is change. And so, what we want to do is to be able to use mathematical functions to create models and predict change. And not only model and predict change, but see if we can find solutions to the problems that change causes in the world today. So what we're going to do is we're going to start with a video, kind of a unit opener about change and the different types of change that we see in the world and how math can possibly help us to manage change.
If there's one thing that remains constant in the world, it's change. Everywhere you look, nothing seems to stay the same for very long. Some things change really quickly, while others change much more slowly. We can describe and model changes to better understand them, and even predict future changes. Populations of cities, countries, and regions are always changing, increasing or decreasing over time. Both population growth and decline can happen suddenly. There may also be peaks and valleys to growth patterns, and some populations grow or decline at a constant rate. Different factors can contribute to population change. In China, a family planning policy limited the number of children a family could have, and this initially caused a rapidly growing population to slow down. In the past, many African countries experienced a decline in population because of a high incidence of disease. But now, populations in the sub-Saharan African countries are expected to double by the middle of the century. What other factors can affect population change? How can you model these changes? Think about what happens when you drop a ball. Well, it bounces, of course, but what happens when it bounces again and again? When you drop a ball from a higher place, like a bridge or a building, what do you notice about the way the ball bounces? This little fellow sure loves to play outside, but he also likes to run to the neighbor's house, and sometimes even farther. You want to put up a fence so you don't have to worry about him running away. But there are a lot of different types of fences, and different ways to put them up, and the materials and labor to have one installed cost money. To save money, you can take advantage of the side of the house. Given a certain amount of materials, how can you build a fence so that it encloses the largest area possible? Although at first it may seem impossible to figure out how something is going to change, quadratic functions can help you model different kinds of changes over time, and even predict what may happen in the future. What types of changes would you like to investigate and explore?
Okay, so if you go to Canvas, you'll see that there are two embed documents in your posting today. We have our guided notes for the function machines and function notation. And then there's another embed, which is the functions maze for later today after you complete the graphic organizer. So you can either recreate this graphic organizer in your notebook, you can pop it out and print it, or you can do like I'm going to do here and pop it out and use the Kami app to make your notations on the actual document. Okay, and we'll just have to see how well that works because I know Kami and Canvas weren't working well with each other, but that might be different now. But anyways, what a function is about is modeling and predicting change, and hopefully by modeling and being able to predict change, we can manage change. So functions are all about change. And what a function is, if you see here, is a function is simply an equation, but what separates a function from a normal equation isn't just the function notation that you see here, but also the fact that a function assigns one input to one output, okay? And that's what separates it from an equation. So what we're going to do here is we're going to say that a function can be thought of as a machine, okay? And as a machine, it assigns one input to one output. Okay, so go ahead and either write this in or type it in as I'm doing here. Okay, and so like I said, this is what a function machine, and this is what we call function notation. So if we look here at our first block, we see that it's pointing to the letter F, and so the letter F is going to be the name of the function. Okay, and one of the reasons that we use function notation is because when you are trying to solve multiple problems and writing multiple equations, it's easier to keep track of them if we have different names. So here we have this one, which the name of the function is f, and we're going to say that this is read or said f of x is how we read or say function notation. So this here is f of x. If the letter were G, then it would be G of x. If it were H, it would be H of x. If it were Q, it would be Q of x, and so on. So it is read and said f of x. Okay? So the x is going to be the input to the function. So any number you choose to input is going to go here. And then this entire portion over here, the f of x, is going to be what we call the output of the function. And it's also going to be y. So sometimes you're going to see function notation, which is going to be f of x equals a certain rule over here. Other times you might just see y equals a certain rule. And that's because what we're going to see probably not tomorrow but the day after is that these functions create ordered pairs that we can put on a graph and actually make a graph or a picture of the function. Okay, so here we have the input to the function. We have the name of the function. It's read or said f of x. This is the output to the function. And this here is what we call the function rule. And this is where the change occurs. Change occurs according to the function rule. So let's look at what happens here. This is our function machine down here. So if we have the number 2, like it says here, to find and illustrate f of 2 and f of negative 1 using the function machines below. If we say f of 2, that means that 2 is going to be the input to the function. So 2 is the input. Now here inside the machine, we have our function rule of 3x plus 4. And like we said, this is where the change is going to occur. Because as we have here 3x plus 4, we're simply going to take and input the 2, because that is our input, into the function rule and add that to 4. So using mental math, 3 times 2 is 6, plus 4 is 10. And so my output is going to be 10. So you notice how you had the input of 2. It went into the function. The function rule changed that 2 into a 10. And that was the output. Okay, so same thing over here. If I have negative 1, that's going to be my input to the function. Again, I have the same function rule of 3x plus 4. When negative 1 enters the function, okay, so 3 times negative 1 is negative 3. Negative 3 plus 4 gives me an output of 1. So notice there, a change occurred. The number negative 1, which was my input, was changed into a positive 1 because of the function rule. So that's how we use functions to model and predict change. Okay? So that's what a function is all about, is modeling and predicting change and using inputs and outputs to model and predict that change. All right, so what we're going to do now is get a little bit of practice doing inputs and outputs to a function. So if you go back here to Canvas, right here, this is going to be the function maze, which you're going to do today. And you're going to go from, like always, go from start to finish. Okay, so notice how each of these has function notation, how it says f of x equals 3x minus 8, find the f of negative 3. And what that basically means is every place that you have an x in your function, you're going to input the negative 3. Okay, so I'm going to pause this video momentarily and switch my my tablet here so I can write on the canvas, and we're going to do the first and the second one together so you can get an idea of what it means to do the inputs and outputs using a function. So I'm going to pause briefly. All right, so I'm back with you, and we're going to go to my canvas drawing, and we're going to start with the first one. So the first one was f of x equals 3x minus 8. And here it wants me to find the f of negative 3. So what that means is every place that I see an x, I am going to insert or input the negative 3. So that means this function is going to be f of negative 3 equals 3 times negative 3 minus 8. So the f of negative 3 is going to equal negative 9 minus 8. So the f of negative 3 is going to equal negative 17. All right, so that is the answer to the first one, is negative 17. So then now you'd move on to the next problem, which is h of x equals 7x minus x squared plus 2. Find the h of negative 4. So let me get up a new drawing here. So I have here h of x equals 7x minus x squared plus 2. And I need to find the h of negative 4. Okay, so to find the h of negative 4, I'm simply going to input negative 4 every place that I see an x. Now, what you need to be mindful of here is I have a minus symbol and negative 4 squared. So negative 4 squared means negative 4 times negative 4. So that's going to be a positive 16. However, I still have that minus symbol there. So that's actually going to be negative 28 minus 16 plus 2. Oops. So negative 28 minus 16 is a negative 44 plus 2. So the h of negative 4 equals a negative 42. Now, I know that there are probably some people out there that are thinking you can just look at this and do all of this in your brain and keep all these calculations in your head, and you've got that calibrated eye that says I can just do all this with looking at it. And that might work for today. However, tomorrow, when we do composite functions, that is not going to work. So you need to be accustomed to showing your work and showing your steps and showing how you input the negative 4 into this function and how the function changed your negative 4 into a negative 42. Because if you don't show your work, it's going to be very difficult for you to find mistakes, and you're going to find yourselves getting lost, especially tomorrow when you are doing composite functions. Okay, so what we're going to do then is I've done the first two for you. So we did negative 17, and then the h of negative 4 here was a negative 42. So now that brings you over to g of x equals x squared minus 3x plus 4, and finding the g of 0. So I'd like for you to work the rest of these on your own and make your way to the happy face at the end where you finish, and upload a copy of your work for me to look at. Also, I'd like to see a copy of your notes as far as how you did this graphic organizer, if you used Kami for it, or if you opted to write it out in your notebook. Okay, as always, if you have a question or need clarification, I will be on Google Meet from 10:45 to 11:45, and you can always email me. All right, have a great day, everybody. Thank you for listening. And I look forward to tomorrow when we can get into composite functions.